Hello students. Today in this session we are going to learn chapter 6 electromagnetic induction and chapter 7 alternating current. Overall what are all they have given and deleted in this chapter we'll see, and the formulae which are all you have to focus this both the chapters and the Phasor diagram, graphical representation, these and all we can see. So now let us see the chapter content for this year 2020-2021 from the chapter electromagnetic induction. See, electromagnetic induction, Faraday's law, induced EMF and current, Lenz's law, eddy current, self-inductance and mutual inductance. Actually, from this chapter, they have not deleted any single topic, right? Now, alternating current from the 7th chapter, alternating current, peak and Rms value of alternating current voltage, reactance, impedance, LC oscillations of qualitative treatment, LCR series circuit resonance, power in AC circuits and AC generator, transformer which is also there. What are all they have deleted for this year 2020-2021, that is power factor, wattless current. That is only they have deleted from this chapter. Yes students, know the formulae which is from electromagnetic induction. See, these are all the formulae which is from electromagnetic induction. First one is magnetic flux. So magnetic flux denoted by phi, which is equal to B vector dot A vector, that we can say which is equal to BA cos theta. The SI unit of magnetic flux, Weber. Faraday's law of electromagnetic induction. The Faraday's law of electromagnetic induction which is equal to modulus of sigma is directly proportional to d phi by dt. So Lenz's law gives only the opposite direction, so that which is equal to minus d phi by dt. Induced EMF which is set up across the ends of the conductor, that means we have the different methods of production of induced EMF, right? So by changing magnetic field, by changing area, like that way, we have the formula that is BLV cos theta, and changing theta alone, if suppose you are changing the orientation only, then you will get BNA omega. How we got BNA omega? That is minus d phi by dt by applying Lenz's law, which is equal to minus d by dt of phi value, which is equal to, we get it BNA cos omega t. BNA cos omega t, the cos omega t which is differentiated means we will get sin omega t. Okay, omega sin omega t is the differentiation of cos omega t. So we get finally that BNA omega. The next one is self-induction. Self-induction which is nothing but phi which is directly proportional to I. Which means what? The phenomenon of electromagnetic induction or the EMF of a coil due to the change current, or we can say the magnetic flux which is linked with the same coil. The magnetic flux linked with the same coil, so that phi is directly proportional to current or I, that means EMF. So phi which is equal to Li. Here L is the proportionality constant for the self-inductance. In the same self-inductance coils, we can say for the energy stored in a current carrying conductor also, E which is equal to half Li square, and self-inductance for long solenoid. For that derivation, the final answer L which is equal to mu naught N square La. So this is for the three formula which is for self-inductance. The same way we have the mutual inductance. The mutual inductance we can say that the phenomenon of induction of EMF in a coil which is due to change in the current or the magnetic flux linked with the neighboring coil, the next coil. So phi 2 is directly proportional to I1. The phi 2 which is the flux, magnetic flux is changed in one coil is affecting another coil. So that phi 2 which is equal to, we can say M21I. So this M21 is the proportionality constant of mutual inductance and also mutual induction. And for long solenoid, for the mutual induction, M which is equal to, the derivation final answer says that mu naught N1 N2 AL. So the eddy currents, we know that eddy currents. So the eddy currents given when the magnetic flux linked with the conductor changes. So we can call it as that eddy current, or we can say that is the current which gives for always production in the plane of the perpendicular to the direction of the magnetic field. So it has a lot of applications also, and we can say there is the electromagnetic damping, brakes, right? So these are all some of the induction motor and all also we can say for the induction eddy current, children. So next one is they have given in our book AC generator. The principle for the AC generator is EMI, that is electromagnetic induction. We got E which is equal to NBA omega sin omega t, which is for the orientation, right? That is the instantaneous value of the EMF which is produced, right, in the AC generator. So these are all the formula from the alternating current. If you know these Bay formula, then it is very easy for you to resolve and know about the phasor diagram and all the graphical representation. Let us see that. See, I which is equal to Im sin omega t, or we can say I which is equal to Im cos omega t. That we can say that for the current. So this is the alternating current whose magnitude which is changed with the time. So directions versus periodically the direction will get changed. E which is nothing but the EMF. So we can say that the EMF of that alternating voltage E which is equal to Em sin omega t, or E which is equal to Em cos omega t. Here the I average which is equal to 2 Im by pi. The value is 0.636 Im. So that 0.636 Im we can say, and IRMS value, so IV that is equal to I naught by root 2, that IRMS value which is equal to we can take 0.707 Im, right. Now we can see the AC alternating current through an inductor, capacitor, how will be the graphical representation. So AC through an inductor, we can take that AC through the inductor as the graphical representation, that is EMF will be behind pi by 2. So XL, we can say that the XL is the inductive reactance, right. If suppose you have taken with the frequency and the inductive reactance, it will be directly proportional. So that only the straight line came, right. So here AC through a capacitor will come. This will be the current leads the EMF by phase pi by 2. So XC is the capacitive reactance. Now one by one the phasor diagram we can see that. The phasor diagram, resistor in AC. The resistor, only resistor, which means you can have, there is no phase angle. Both are in the same angle. There is no angle, same phase. So VR and I which is there in the same phase means, so it will be go in the same direction. There is no change in the orientation or the angle. Now B which is for, this is the phasor diagram for the inductor. So inductor means the phase angle which is VL leads to I. So the VL EMF is leads 90 degree pi by 2. So it is going ahead, right. So that's why which is in this direction. And here see the pure capacitor. The capacitor, we can say the phase angle which is 90, but the I leads VC. So I which is leads, the current leads pi by 2 by the EMF. Okay. So this is the diagram for the LCR. That is inductance, capacitance and the reactance or resistor for the series. If suppose 3 which is there in series, we can get the value that is I leads. V if suppose XC is greater than XL. XC which is greater than XL means I will be leads. And I, the current will be lags behind V when XC is less than XL. So if you know all the details, in details things which is there in alternating current, then it is very easy for you. Note it down in your note and repeatedly draw and practice it. Yes, students. Now question number 1. Predict the direction of induced current in the situations described by the following diagrams. See, observe this 4 diagram. Diagram A, which is there with the coil, and nearby they kept one magnet. The direction of the magnet also they have given, and south and the north pole. In this way it has given. And B also, you have two coils, in between you have the magnet, the direction it shows to the first coil. And see the C diagram, observe it. This is this coil which is connected with one cell, right? And this is nearby one more coil they kept. Option D, in that also in the same way it is connected. And see the direction, and they have given direction or not also. Because you are going to predict the direction of the induced current in these situations. How it will be the induced current? Observe the diagram, children. See, by observing and seeing that they have given the way of coil and the magnet, you may understand that the Lenz's law, which gives the direction of the induced current in the closed loop, right? So, the given diagrams which shows the direction of the induced current when the north pole of the bar magnet is moved towards and away from the closed loop. And here the south pole which is moved inside and away. So, by that way of applying the Lenz's law or the direction of induced current, we can easily say that here for the first diagram, the induced current which described from the direction of Q or P, right? Because of the south pole which is going inside. So, we can say that this is from Q or P, the direction given that Q or P is the direction. And also we can say for diagram B, see the diagram B, for this the coil 1 which gives P or Q. Okay, P or Q, in that way it is moving south, and here we can say XY direction, right? So, XY Z it is moving. So, here P or Q, or we can say here for that next diagram XY, sorry, XZ, in this way it will move, okay, the same way it will move. And for C, diagram C, see the diagram C, observe it, it will move. See, by seeing the diagram which is connected with the cell, you may understand that how it will be also. So, by that way we can say it will move in the direction of YZX, right? So, this will become YZX. So, this is the direction of current for this coil. And for this coil, the direction of the induced current in this situation, we can say that ZYX. So, here ZYX, in this way it will be moved, right? So, by applying Lenz's law, you can understand that, children, the Lenz's law which gives the direction of the induced current in the closed loop and the direction of the induced current when north pole of the bar magnet is moved towards and away from the coil. But by that way we understood, and seeing the direction and the poles, you have to understand and correctly predict and write the induced current in these situations. So, question number 2, current in a circuit falls from 5.0 to 0.8 ampere in 0.1 second. If an average EMF of 200 volt induced, then given an estimate of the self-inductance of the circuit. For this, the base formula E, which is equal to, we can say that minus L into dL by dt. So that from that we can convert, we need that self-inductance, right? So the self-inductance L, which is equal to minus E by dL by dt. So by applying the value, we will get L value. Directly we can apply the EMF they have given minus of 200 whole divided by, they have given minus 5 divided by 0.1. So by simplify this, you will get 4 Henry. Okay, so this is the self-inductance value. And for Q3, when a coil which is rotated in a uniform magnetic field at constant angular velocity, then will the magnitude of the induced EMF set up in the coil be constant or not? Why? See, By analyzing the statement, you will get when a coil which is rotated in a uniform magnetic field at a constant angular velocity also. That time, the magnitude of the induced setup in the coil, induced EMF setup in the coil will not be constant. No, it will not be constant because the induced EMF will vary with time. So we can say that it will be vary with time, right? Because of, we can say that the value will be getting varied. Because of the sinusoidal due to the change in the orientation of the coil with respect to the magnetic field, right? So question number 4, a light metal disc on the top of an electromagnet is thrown up as the current is switched on Y. See, without any doubt, we can say that due to because of eddy current. Due to eddy current. See, a light metal disc on the top of an electromagnet is thrown as the current which is switched on because of the eddy current, and we can say that the current which is produced opposite polarity on the lower side of the disc, so that only it is throwing up. And next question number 5, a coil Q which is connected to a low voltage bulb B. So this is bulb B, this is the low voltage bulb which is connected, the coil is connected and placed near another coil P as shown in the diagram. So this is connected with the AC source, right? Now you have to give reason to explain the following observations. First one is the bulb B which lights well, and the bulb B gets dimmer if the coil Q which is moved towards left. See the situations, observe the situations, children. First one is they have given the bulb B lights. The bulb B lights because of, we can say that, the EMF which is induced in the coil due to the change in the magnetic flux. EMF induced in the coil due to the magnetic flux crossing through the coil. And the second question they asked about, the bulb gets dimmer. If suppose the coil Q is moved towards left, means we can say that because of the mutual induction. So we can say that due to the mutual induction of the coil, it's going towards left, and also we can say that because of the induced EMF of the coil Q, which will be getting decreased. So it will be get decreases with the separation between the coils. Right. So because of that, the bulb get dimmer. If suppose you moved the Q, right? So due to the mutual induction, this is happening, and also the induced EMF of the coil Q will get decreased, right? Now the next question, define mutual inductance and write its SI units. Subdivision B, derive an expression for the mutual inductance of two long coaxial solenoids of same length with one over the other. The third subdivision, in an experiment, two coils C1 that due to a change in current through the coil C2. So this is a long answer question. So usually we have a long answer question like subdivisions. The subdivision will give the separation of marks, like define mutual inductance and write its SI unit maybe like 2 marks. And this one is for the derivation of the mutual inductance of the long coaxial solenoid for 2 marks. And the experiment will give, due to the change, the C1 coil, due to the change in the current in coil C2. All the 3 which is together for the mutual inductance of the coil. First, you must know what is mutual inductance. The definition you have to write. The definition says that the magnetic flux linked with one coil, you may see the diagram, from that also you can understand. The magnetic flux EMF, that is phi, which is linked with one coil, when the unit current, the current which is passing through the other coil. So it depends on another coil. So phi, which is directly proportional to I. So phi, which is equal to Mi, we can say that the M is the proportionality constant for the mutual inductance. And the SI unit of the magnetic flux, the SI unit of mutual inductance, which is Henry, H or Weber per ampere. The second subdivision which says that, so this is the phenomenon, that means we can say that the mutual inductance of the coil, see mutual inductance between the 2 long coaxial solenoid which you are seeing on the screen, the diagram. So the diagram says that as the magnetic flux linked to the second coil when unit current is flowing through the first coil, right? The definition says the same term. So as per the phenomenon by virtue of which a coil resists any change in the strength of the current in its neighboring coil, then B2 which is equal to, we can say that mu naught N2 I2, right? See, the B2 which gives the magnetic flux, the magnetic field of second coil which is equal to mu naught N2, number of turns in the second coil, the current which is passing through the second coil, right? Now, the flux linked with the inner solenoid, that means the coil 1. Then we can say that the flux 1, 2 which is equal to B2, it will be depending on B2 pi r square NL, right? Now, phi 1, 2 which is equal to what we said, phi 1, 2 which is equal to B2, we said no, the B2 value we are applying here. So, B2 value which is N1, N2 pi r square L. So, by applying the value you will get it, right? So, M12 which is the mutual inductance of the solenoid. Got it, children? So, next third subdivision, in an experiment, 2 coil C1 due to a change in current through the coil C2, right? So, the magnetic flux linked with the coil, that phi, we can say that the phi value is linked with the coil C1 due to the current I2 because of the mutual inductance, right? So that the phi 1 which is directly proportional to I2, phi 1 which is equal to Mi2. So that d phi by dt, change in flux will give the change in the other coil. So that is only the statement says no. The statement says change in the flux is directly proportional to the change in linked with the coil which is change in the current I2, right? So that only d phi 1 by dt which is equal to m into di2 by dt. So that E which is equal to minus of m into di2 by dt. His next question, what are eddy currents? How are they produced? And describe briefly 3 main useful applications of eddy currents. Like that, if they ask, you have to write what are eddy currents. The definition says that when the magnetic flux linked with the conductor, that will changes. What are the changes which is occurred? So it will give eddy current. We can say that that is called as the eddy current. Okay. Now, the eddy currents are always produced in a plane perpendicular to the direction of the magnetic field, and also we can say that it shows that the heating and the magnetic effects, right? So, when a conductor in a bulk which is kept in changing magnetic field, the eddy currents are induced. And what are the applications? 3 main applications we said that the magnetic brakes in trains, right? The magnetic brakes which are all in trains, in some electrically powered trains, strong electromagnets are situated above the rails. So when these magnets are activated, the eddy current are induced in the rails. These current give the opposite motion of the train. So due to the absence of the mechanical leakage or the braking effects should be strong. So here the magnetic braking in trains it is mainly applied, and the electromagnetic damping we can say that. So certain galvanometers have the fixed core made of a non-magnetic metallic material, right? So when the coil of galvanometer oscillates, the eddy currents are generated on the core. That is also in the opposite motion. So that as a result, the coil comes to rest quickly. So that here in the electromagnetic damping, we can use it. So for a quick response. And the electric power meters, here in the electric power meters, the shiny metallic disc in the electric power meters which will rotate because of only the eddy current, right? The next question, define capacitive reactance and write its SI unit. See, we can say that the capacitive reactance, the opposition to the flow of current in AC circuit which offered by the capacitor XC which is equal to 1 by omega C. And the SI unit we can say that ohm. Right. Next question. Plot a graph showing variation of capacitive reactance with a change in the frequency of the AC source. See, it is inversely proportional. Omega, which you can take it in x-axis, and in y-axis you can take XC. Then the graph will be shows like this, right? So next question, define the term Rms value of the current and how it is related to the peak value. See, the square root of average value of square of alternating current, which we can call it as root mean square, that is IRMS or RMS value of alternating current we can say. How it is related with the peak value, that is IRMS which is equal to I naught by root 2. So the I naught by root 2 value which is equal to 0.707 I naught, right? The next question, an alternating voltage which is given by V which is equal to 140 sin 314T. So which is connected across a pure resistor of 50 ohm. We have to find the frequency of the source and the RMS current through the resistor. Now, they have given the value that is 2 pi. We know that the formula 2 pi frequency which is equal to omega. So, the omega value as they have given 2 pi f which is equal to 314 radian per second. From that we can take the value. And section B question is the RMS current through the resistor. So section B, so IRMS which is equal to VRMS by R. So where we can say that VRMS which is equal to V naught by root 2. So that we can write IRMS which is equal to 140 whole divided by root 2 into 50. By simplifying this, we can get 1.98 ampere, or we can write that is approximately equal to 2 ampere. Okay. So this is the IRMS value. Yes. This question, diagram shows that the variation of resistance and reactance versus the angular frequency. Resistance, reactance and with the angular frequency versus both we are having the phasor diagram or the graph we can say. So identify the curve which corresponds to inductive reactance and the resistance. Say for the inductive reactance we can say the curve B, because inductive reactance which is directly proportional with the frequency. Okay, so the straight line is the curve for the B, inductive reactance, and we can say the curve C which is for the resistance. Okay, this is for the part A question. Part B, show that series LCR circuit at resonance behaves as a purely resistive circuit, and you have to compare the phasor diagram, that is the phase which is relation with the current and the voltage in series of the LCR circuit for XC is greater than XL is greater than XC and XL which is equal to XC by using the phasor diagram. That is only we are seeing that. See the two phasor diagram, it shows for XC is greater than, XL is greater than XC means that is inductive reactance is greater than capacitive reactance, then the phase difference is phi. That is only you are seeing through this diagram. The phase difference between that VL that will be is greater than VC then. Got it? So for the second one is they have asked for XL which is equal to XC. So that we can say that VL which is equal to VC. So the phase difference is 0. There is no phase difference for that. Okay. Here the third part of the question they asked, what is an acceptor circuit and where it is used? See, acceptor circuit which means we can say the LCR circuit in series, and it is used in tuning mechanisms of radio, television and all which we are using, that is series LCR only. So tuning mechanism we are using, that is the acceptor. Series of LCR circuit is the acceptor. Now we will discuss about one case study. See, they have given the definition of mutual inductance. The mutual inductance between the two coils is defined as the property of the coil due to which it opposes the change of current in the other coil, or we can say that in the neighboring coil, right? So when the current in the neighboring coil changes the flux set up in the coil, and because of this changing flux EMF is induced in the coil, which is called mutually induced EMF, and this phenomenon which known as mutual inductance, right? So the value of a mutual inductance M, which is depends upon the following factors, that is number of turns in the secondary coil or neighboring coil we can say, and the cross-sectional area of two coils, right? So when on a magnetic core, two or more than two coils are wound around the coil are said to be mutually coupled, right? So the current when passed in any of the coil wound around the magnetic core will produce a flux which links all the coils together and also the one in which current is passed. Hence, there will be both self-inductance EMF and mutual inductance EMF in each of the coil. The best example for the mutual inductance is the transformer, which works in the principle of Faraday's law, that is of electromagnetic induction. Faraday's law of electromagnetic induction says that the magnitude of voltage is directly proportional to the rate of change of flux, which it explained in the topic of Faraday's law of electromagnetic induction. So this is only they have given as a case study paragraph about the definition of mutual inductance and what is the character which depends on the following factors and the link between the mutual inductance and the self-inductance. So what are all the questions they were asked for the multiple choice questions? We'll see. So question number 1, the phenomenon due to which this is an induced current in one coil due to current in neighboring coil is, they have given the options. Option A, electromagnetism. B is susceptance. C, mutual inductance. D, steady current. See the phenomenon due to which there is an induced current in one coil due to the neighboring coil means we can say option C, mutual inductance. Question number 2, mutual inductance between two magnetically coupled coil depends on A, permeability of the core material, option B, number of turns of the coil, and option C, cross-sectional area of their common core. Option D, they have given all of the above. See, the mutual inductance between the two magnetically coupled coil depends on all the above only. Option A, B, C. All the above, that is permeability, number of turns, and also the cross-sectional of area. So, option D, all the above is the answer. Question number 3. Which of the following is the unit of inductance? Option A, ohm. Option B, Henry. Option C, ampere turns. Option D, Webers per meter. So, for the unit of inductance is option B, Henry is the answer. Question number 4. Which of the following circuit elements will oppose the change in the circuit current? Option A, capacitance. Option B, inductance. Option C, resistance. And option D, all the above. See, the inductance is the circuit element will oppose the change in the circuit current. So, option B, inductance is the answer. If in an iron cored coil, the iron core is removed so as to make the air which is cored coil, the inductance of the coil will be, option A, it will be more, option B will be less, option C, the same, and option D, none of this. Answer is option B, it will be less. The inductance of the coil will be less. Yes, students. So far we have learned from this session electromagnetic induction and alternating current. From this, the various questions we have discussed. They have asked repeatedly from the year of 2015 to 20. Previous year board question paper and the sample question paper we have taken and resolved it. Please see that again and again and work it out in your paper and practice the phasor diagram of inductance, reactance, and the capacitance, resistor, right? And the LCR series circuit, AC generator. So these are all you have to study and focus in class 7th chapter and 6th chapter, Faraday's law, eddy current, and all the overall things what we have discussed, you can practice well. Thank you, students.